Hello everybody, this is Dr. Ritu Singh from Basic Science Department, and today's topic of discussion is again electrochemistry. It is the third lecture of electrochemistry. So in electrochemistry we have already done two lectures of electrochemistry. In that we have done what are electrochemical cells. So first, what is electrochemistry? Then what are the energies which we are concerned about in electrochemistry? They are chemical and electrical energy. Then what are electrochemical cells? We have got two types of electrochemical cells, galvanic and electrolytic. Then the example of electrolytic cell is the process of electrolysis, from which we came up to two laws of Faraday's. Then what are galvanic cell? The setup of galvanic cell. Then about the electrode, what is an electrode, then what is an electrode potential, then because we cannot calculate the absolute value of electrode potential, so we require reference electrodes. So next we discussed reference electrodes, and after reference electrodes we discussed about electrochemical series. So these are the topics which we have already taken care. Today we are going to start with how cell constant depends upon the thermodynamic parameters, or what is the relationship between cell constant, or sorry, cell potential. It is not constant, it is potential, cell potential and thermodynamic parameters. Thermodynamic parameters. So how E cell is related to thermodynamic parameters. If we talk about thermodynamic parameters, then normally we consider the main three, that is G, H and S. G is Gibbs free energy. H is enthalpy, and S is entropy. So Gibbs free energy, whenever a system undergoes a change in state, the energy which is possessed is Gibbs free energy, and depending upon whether the work is done by the system or work is done on the system, then the energy is taken up as negative or positive. So when the system is doing work, the energy is expanded. So in that case delta G is negative, but when work is done on the system, then it will be a positive value. It will go for Gibbs free energy, enthalpy and entropy in all the cases. Work is done on the system or work is done by the system. Now enthalpy is the energy when pressure is constant. Energy when volume is constant is either given by E or it is denoted by mu. So whenever energy is expressed in terms of E or mu, that means the volume is constant, but when enthalpy is energy when pressure is constant, that is known as enthalpy. And entropy is the randomness of the system. Randomness, and if we see the all the process which take place in nature, in all those processes which are taking place in nature or in natural process, entropy is always going to increase. So for a spontaneous process, entropy is always positive, enthalpy is negative, and delta G is also negative. So this is the condition when the process are natural. So for a natural process or for a spontaneous process, Gibbs free energy, the change in Gibbs free energy, or we can say that delta G is always negative, enthalpy is always negative, but entropy is positive. These are changes, change in Gibbs free energy, change in enthalpy and change in entropy. So these are the thermodynamic parameters which we are going to consider. Now the first parameter which we consider is the relationship between cell potential and Gibbs free energy. Now, in electrochemistry, the change which we are studying is here a chemical energy is converted into electrical energy. So, whenever this conversion is taking place, the work is done. So, the net work done is given by E into Q, where E is EMF and Q is quantity of electricity passed. So, E is the EMF and Q is quantity of electricity passed. Now, Q, the quantity of electricity passed, is equal to NF, where N is the number of electrons, how many electrons are exchanged, and F is Faraday's constant. So, N is number of electrons and F is Faraday. Faraday is a charge on 1 mole of electron, which is equal to 96485. This is the exact value of Faraday's, but for convenience, we take it as 96500. So, the quantity of electricity passed is equal to NF. Now, if I substitute this in this first equation, then I get net work done is equal to NFE. We can write, because this E is potential, so we can write it as cell potential. So, the net work done is equal to NFE cell. Now, whenever the system is going to do work, there is change in energy, and because the system is doing work, so the energy is going to decrease, and the change in energy is given in terms of Gibbs free energy. So, the net work done is equal to the amount of energy which is changed, and because the system is doing work, so energy is going to decrease. So, the net work done can be given by minus delta G, and G is Gibbs free energy. Now, if we see these two equations, one side is equal, so the other side is also equal. That means minus delta G is equal to NFE cell. So, this is the equation by which Gibbs free energy, which is a thermodynamic parameter, is related to cell potential. Now, here when delta G is negative, then the process is spontaneous. When delta G is positive, the process is non-spontaneous, and when delta G is 0, that means that is the condition for equilibrium. So, this is how by this relation, this is the relation where cell potential is related to Gibbs free energy. The second correlation is between cell potential and entropy. And entropy is the randomness of the system, disorder. So, all the normal processes which take place in nature are irreversible, and the entropy of the universe, it keeps on increasing. So, whenever a spontaneous process is going to take place, the entropy is always going to increase. So, the relationship next is relationship between cell potential and entropy. Now, delta S minus delta S is equal to minus delta G over delta T at constant pressure. This is given. Now, we know that delta G is equal to minus NFE cell. So, if we substitute the value of delta G here, we get del minus NFE cell over del T at constant pressure. N and F will be constant because F is Faraday and N is number of electrons. So, for a reaction, it is going to remain same. So, we can take it out, NF del E over del T at constant pressure, and this is equal to minus delta S. So minus minus get cancelled. Delta S is equal to NF del E over del T at constant pressure. Here in thermodynamics, E means energy, but we are taking we are into electrochemistry, so here E is not energy. E here is cell potential. So this is the equation by which entropy is related to this cell potential. So this is the second thermodynamic parameter, which is entropy. The third thermodynamic parameter to which the cell constant is related is enthalpy, which is E. Enthalpy is nothing but energy, but at constant pressure. So that is given by H. Here we know that delta H is equal to delta G plus T delta S. So this is a equation by which the three parameters are related. So we know that delta G is minus NF E cell, and we have delta S is equal to NF del E over del T at constant pressure. This we have already derived just now. So we put up the values of delta G and delta S into this equation. We get minus NF E cell plus T NF del E over del T at constant pressure. So taking NF as common, I get E cell plus T del E over del T at constant pressure. This is delta H. Now if I write this equation in terms of E cell, then minus delta H over NF plus, so this should be minus, plus T del E over del T at constant pressure. So this is the equation which is relating cell potential and enthalpy. So these are the three parameters, thermodynamic parameters, which are related to one another. So what are the parameters? So cell potential is related to thermodynamic parameters. The first is delta G is equal to minus NF E cell. Then delta S is equal to NF del E over del T at constant pressure. Then E cell is equal to minus delta H over NF plus T del E over del T at constant pressure. So this is how the thermodynamic parameters, they are related to cell potential. We have another one more thermodynamic parameter, which is an equilibrium constant. So the last is cell potential and equilibrium constant. Equilibrium constant. Now if we take up a general reaction which is A, B, B giving C, C plus D, D. So in thermodynamic in equilibrium constant, we have a term which is quotient Q. It is given by C raised to the power C, D raised to the power D, A raised to the power A, and B raised to the power B. Now here minus delta G is equal to minus delta G naught minus RT ln Q. This is a term which we know. Now if we put up the values here, then delta G is equal to minus NFE cell, and minus delta G can be written as RT ln K, and K is the equilibrium constant. So if I put up the this is naught. So if I put up the value of J, delta G and delta G naught, then I get, this is NFE cell is equal to RT ln K minus RT ln Q. And at the last, Q is replaced by this term. So I am not writing it again and again. I divide this equation by NF. So when I divide this whole equation by NF, I come to a term which is E cell is equal to RT ln K over NF minus RT ln Q over NF. In the next step, I convert this ln into log. So when I convert ln into log, I have to multiply by 2.303. So it is 2.303 RT over NF log K minus 2.303 RT over NF. So this is the term. Here 2.303 RT over F. So R is a gas constant which is 8.13. T is the temperature at whatever, if it is a normal temperature, then we are going to put up the normal temperature. If some temperature is given, we are going to put up that temperature. So that is constant for a particular case. F is Faraday's constant. So if I calculate it, it comes out to be 0.0591. So this equation can be written as E cell is equal to 0.0591 N log K minus 0.0591 N log Q. So this is how cell potential is related to equilibrium constant, and in place of Q, 0.0591 N log K minus 0.0591 N log. I can write C to the power C, D to the power D, and A to the power A, and B to the power B. So the coefficients of A, B, C, D, they are taken as powers. So this is the fourth thermodynamic parameter which is related to cell constant. So cell constant, what is a cell constant? We have got, it is actually a potential difference when the current is flowing from the circuit. And what is EMF? It is also a potential difference when no current is flowing through a circuit. So if I take up a whole of the electrochemistry, then electrochemistry we study the conversion of chemical energy to electrical energy or electrical energy to chemical energy. What is an electrode? Electrode, when metal is in contact with its ions, that is an electrode. And what is an electrode potential? When metal is in contact with solution of its ions, it can undergo oxidation or reduction. That means it has got the capacity to lose electron or gain electrons. And when it has got, when there is a process of oxidation and reduction, then an potential difference is created, and that is known as electrode potential. We have got two types of electrode potentials, EMF and cell potential. Then we discussed about the electrochemical series, where the metals, they are arranged in an order of increasing reduction potential or decreasing reduction potential, but they are arranged, the metals are arranged on the basis of electrode potentials. So normally in between the condition or the arrangement is, in between we are having hydrogen. Above hydrogen are the metals which have got negative electrode potential, and below nitrogen is the are the metals which have got positive electrode potential. So the negative ones can be easily oxidized and the positive ones are easily reduced. And we have got some more properties, and by using the electrochemical series, we can calculate cell potential. We can know whether the reaction is feasible, we can know whether the reaction is spontaneous or not, and then we can determine the oxidizing and reducing property of different metals. So that is the silent features or application of electrochemical series. And here in this lecture we have discussed how cell potential, or we are discussing how cell potential is related to thermodynamic parameters, and the thermodynamic parameters. So, how thermodynamic parameters are related to cell constant, and we have discussed the 4 thermodynamic parameters, which is delta G, delta S, delta H and equilibrium constant. So, next we come to an important equation in electrochemistry, and that is your Nernst equation. Now, Nernst equation, it tells about how cell potential is dependent upon the concentration of electrolyte, or how the concentration is going to vary with the cell potential. Now, we know that delta G, at any instant, delta G is proportional to the concentration and the reaction quotient. So, that is given by the equation delta G is equal to delta G naught plus RT ln Q. So, at any instant, delta G is dependent upon, or Gibbs free, change in Gibbs free energy is dependent upon the concentration and the reaction quotient, and delta G is not 0 initially, but as the reaction proceeds, the value of delta G keeps on changing, and when delta G is 0, that means now we have arrived to the condition of equilibrium. Now, we know this term where delta G is equal to delta G naught plus RT ln Q, where delta G is Gibbs free energy, delta G naught is again Gibbs free energy at constant in a standard condition, and Q is the reaction quotient. Now, we know, or we have just now derived, that delta G is equal to minus NFE cell. So, this is under non-standard condition. If we have to write down in a standard condition, then it is minus NFE cell. So, we substitute both the values into this equation. So, I get minus NFE cell is equal to minus NFE cell naught plus RT ln Q. This can also be written as NFE cell is equal to NFE naught cell minus RT ln Q. Now, I divide this equation by NF throughout. So, I get E cell is equal to E naught cell minus 2 RT NF ln Q. Now, I convert ln into log. So, when I do the conversion, I get E naught cell minus 2.303 RT over NF log Q. Again, this term 2.303 RT over F again is a constant value, and this is equal to E naught cell minus 0.0591 N log Q, E cell. So, this is Nernst equation in terms of quotient. Now, we consider a general reaction, and the general reaction is M is undergoing reduction solid. So, if I have to write it in terms of, or we have to write reaction quotient, it is M solid over Mn positive, or ionic form of the matter. So, with this equation, or with this general reaction, I write the equation which I have derived. So, it is E cell is equal to E naught cell minus 0.0591 N log concentration of solid species divided by concentration of ionic species. Now, in equilibrium constant, we have read whenever concentration of solid species is taken, the entity is taken as unity. So, this concentration of solid species is taken as unity. So, the equation becomes E naught cell minus 0.0591 n log 1 over mn ionic form. Now, this is again a form of Nernst equation. Here this Nernst equation is written in terms of negative sign. So, Nernst equation can be written in terms of negative sign or can be written in terms of positive sign. So, I can write it with positive sign as well, where E naught cell is equal to E cell is equal to E naught cell plus 0.0591 n log. So, these are the two forms of Nernst equation. One I have written with the positive sign, the other I have written with the negative sign. So, now if I have to apply Nernst equation to some cell, then the only problem in this numerical is we don't know whether the cathode is taken or we get confused whether the metal on the cathode will be taken as a numerator or the metal at the anode will be taken as a numerator. So, that is the only problem when we are doing numericals on electrochemistry or Nernst equation. So, if I take a general reaction like Zn plus 2, copper plus 2 and copper. So, copper is undergoing reduction and zinc is undergoing oxidation. And we have already done this, how to represent or how we are going to do cell representation. So, suppose we are having this cell and we have to write down the Nernst equation. Now, if the Nernst equation is written with a negative sign, E naught cell minus 0.0591 n log. If I am writing this equation with a negative sign, then the metal which is taken at anode, it will be taken as a numerator, and the metal which is taken at cathode will be taken as a denominator. So, it is written as Zn plus 2 over copper plus 2. This will be the form of Nernst equation. So, or anode over cathode when the equation is written with a negative sign. Now, suppose I write this equation with a positive sign, then E naught cell plus 0.0591 n log. When I am writing this positive sign, then the metal at the cathode is taken as numerator and metal at the anode will be taken as the denominator. So, this is copper plus 2 over Zn plus 2. So, this is how we have to write down. So, this is the only thing which we have to remember when we are doing numericals on Nernst equation. What is taken as the numerator and what is taken as the denominator. So, if I generalize this equation, then when I am writing it with negative sign, then the metal at anode is top and metal at cathode is taken as denominator. It can also be written in terms of oxidation or reduction. So, here we write oxidation and here we write reduction. And if I am writing it with positive sign, then I have got cathode over anode. So, cathode over anode again means reduction over oxidation. So, this is how we are going to do numericals on Nernst equation. So, this is our Nernst equation. So, if I generalize it, then E is equal to E naught cell plus, I am writing it with positive sign. So, 0.0591 n log reduction over oxidation. So, this is the general form of Nernst equation. Now, by using Nernst equation, we can also calculate the equilibrium constant. Before Nernst equation, we have derived a relationship between cell potential and equilibrium constant. And here, we are also again going to we can again calculate equilibrium constant based on Nernst equation. So, what is that is, suppose I am taking up Zn plus 2 giving Zn plus 2 plus copper. Suppose this is a reaction. If I have to write the value of K, which is equilibrium constant, it is written as concentration of zinc ions into concentration of copper ions divided by concentration of zinc ions into concentration of copper ions. And we know that in equilibrium, the solid entity is taken as unity. So, these two are solid entities, they are taken up as unity. When they are taken up as unity, so this is equal to 1 and this is equal to 1. When these two are 1, then the equilibrium constant is Zn plus 2 over copper plus 2. Now, if I have to write in terms of Nernst equation, then E cell is equal to E naught cell minus 0.0591 n log Zn plus 2 over Cu plus 2. Now, whenever we are considering the condition of equilibrium, then this E naught cell is taken as 0. So, when I take it as 0, then E naught cell is equal to 0.0591 n log, and this is equal to K. So, I write it as K. Then log K is equal to n E naught divided by 0.0591. So, this is the equation by which we can calculate the value of K. So, if I write log here, that means we are going to take anti-log of this equation to calculate the value of K. So, the value of K can be given as K is equal to anti-log n E naught over 0.0591. So, this is one more equation by which we can calculate equilibrium constant, and this is based on Nernst equation. Now, we are going to discuss some applications of Nernst equation. So, in applications of Nernst equation, we have got 5 applications of Nernst equation, and in different based on different applications, we have got different numericals. Now, the first application of Nernst equation is Nernst equation. By using Nernst equation, we can study the effect of electrolyte concentration on the electrode potential. So, how the concentration of electrolyte is going to affect the electrode potential. So, we can calculate by the help of Nernst equation. Suppose I am having 0.01 molar solution. I have got a zinc rod which is placed in 0.01 molar zinc sulfate solution. So, I am having a zinc rod which is dipped into this solution, and the temperature is 25 °C. So, a zinc rod is placed in 0.1 molar zinc sulfate solution at 25 °C, and we assume that zinc sulfate is 96% dissociated. In that condition, you have to calculate the potential, the cell potential. So, the numerical is, we are having a zinc rod which is dipped in 0.1 molar solution of zinc sulfate at 25 °C. You have to calculate the potential of the electrode at this temperature when the zinc sulfate is 96% dissociated. So, if I write the reaction, that means Zn plus 2 electrons will give Zn. This is the general reaction. Now, first thing we have to calculate is we have to calculate the concentration of zinc ions. So, zinc ions, the concentration is given by 0.1 into 96%. This is how we are going to calculate this. So, this is 0.1 into 96 divided by 100. So, this will give the concentration of zinc ions, which is 0.0096. Now, if I write the Nernst equation, then E is equal to E naught. So, I am writing it in terms of negative value. So, minus 0.0591 n log 1 over Zn plus 2. The concentration, the standard cell potential of zinc, is minus 0.76 volts. So, if I put up all the values, this is minus 0.076 volts. The value of N is 2 and the concentration is this. So, if I put up all the values, I can get the value of cell potential. So, this is one application of Nernst equation, where we are calculating cell potential, or we are determining how the cell potential or electrode potential is dependent upon the concentration of the electrolyte. Now, then I consider this is the first application. The second application is we have to calculate the cell potential under non-standard conditions. बंद हो गया क्या सर? So, the second application is to calculate the cell potential under non-standard condition. So, by using Nernst equation, we can also calculate potential of the cell under non-standard condition. So, the non-standard condition means copper, giving copper plus 2, and the concentration is 0.1 molar. This is the concentration of copper ions. Then I am having H plus ions. The concentration of H plus ions is 0.01 molar, and we are having hydrogen gas. The pressure is 0.95 atmospheres, and then we are having a platinum. This is the cell representation. So, if you look at the cell representation, this is the reference electrode is hydrogen, and here we are determining the concentration or cell potential of this. So, we are saying that it is a non-standard condition. If you remember the hydrogen electrode, in that condition the electrode potential of hydrogen electrode is maintained as 0, but there the concentration of H plus ion should be 1 molar, and the hydrogen gas should be passed at 1 atmospheres. Only that is a standard condition, and under that condition the electrode potential of hydrogen will be taken as 0. But here what is the condition? It is a non-standard condition. So, the electrode potential that will be taken as 0, and the copper, the standard electrode potential of copper is 0.34 volt. And again we apply the Nernst equation. So, if I write the overall equation, copper plus H plus ions giving copper plus 2 plus H2. This will be the general equation based on the cell reaction which I have written here. The hydrogen electrode is under non-standard condition because the concentration is 0.01 mole and the pressure of hydrogen is 0.95 atmosphere, which should be 1 atmosphere. Now, if I write the Nernst equation for this case, then it is E naught cell minus 0.0591 n log concentration of copper ions, because it is taken as anode, into pressure of hydrogen divided by concentration of H plus ions. In this we are taking up the pressure, we are taking pressure because the condition is non-standard. N will be taken as 0. Here this is The electrode potential of copper is 0.34 and hydrogen electrode, that will be considered as 0. So if I substitute all the values, I can calculate the cell potential. So this is how we calculate the cell potential under non-standard condition. So this is the second application. Now regarding the third application. Third application is by using the Nernst equation, we can calculate the concentration of any matter. Suppose the concentration of iron is 0.1 molar and the second electrode is of copper, and it is cadmium. And I have to determine the concentration of cadmium ions here. If I write the equation, E is equal to E naught cell plus 0.0591 N log cadmium ions divided by Fe plus 2. So in this case, the value of N will be 2. Here E is given, which is minus 0.02 volts. So the value of E is given and the value of E naught is also given. E naught is 0.04 volts. So value of E and value of E naught is given. If I substitute the value of E naught, then I get minus 0.02 volts is equal to 0.04 volts plus 0.0591 N to log. We have to determine the value of X, and iron is given as 0.1. So if I substitute, after substituting the values, I can calculate the value of X. So this is the third application. In third application, we are determining the concentration of either of the two electrodes. Here we have determined this one. We can also determine for this also. So the third application of Nernst equation is we can determine the concentration of the electrode. Regarding fourth and fifth applications, the fourth application is we can determine the pH. So different equations related to pH we are going to discuss in the next lecture. So we can determine by using Nernst equation, we can determine the pH, because pH is minus log H plus ion. So if we know the concentration of H plus ion, we can take up anti-log and we can get the value of pH. So further equations we are going to discuss in the next lecture. Then fifth application of Nernst equation is we can determine the valency. Valency is the value of N. So if we know the cell potential, we know the standard cell potential, we know the concentrations of the two electrodes, we can calculate the value of N. So these are the 5 applications of Nernst equation. I repeat, we can determine the cell potential, and we can determine cell potential under non-standard condition. Then we can determine the concentration of any electrode, we can determine the pH, and we can determine the valency. Now I would like to discuss a numerical on thermodynamics which is related to thermodynamic parameters, that is delta G, delta S and delta H. So if I have a cell which is platinum, then I have hydrogen gas, and this hydrogen gas, because we are using standard hydrogen electrode, so the pressure is 1 atmospheres. So platinum and hydrogen gas. Then we are having HCl. We are having an aqueous solution of HCl. And the reference electrode which is taken is calomel. So HgCl2 2 plus Hg. Suppose this is a cell. This is a cell representation. Now, in a the standard EMF of the following cell is 0.26699. This standard potential is at pressure 293 kelvins. Then the second one is 0.2699. This is at 303. So we have got two pressures. This is 6. 0.2669. So the standard EMF of the following cell is found to be this and this, that at the first one is at temperature 293 kelvins and the second one is at temperature 303. You have to calculate Gibbs free energy, which is delta G. You have to calculate delta S and you have to calculate delta H. And all the three are to be calculated at temperature 293 kelvins. So this is the numerical. So we are given a cell. In that cell, we know the EMFs at two different temperatures and we have to calculate delta G, delta S and delta H. Now, we can calculate delta G very easily because delta G is equal to minus NF E cell. So N, because we are taking platinum, so when we write the equation, then the number of electron, the exchange of electron will be 2. So 2, so this is minus 2 into Faraday's constant 96500 into cell. So out of these two, it is already given in the numerical that you have to calculate delta G, delta H and delta S at temperature 293. So we are going to put up this EMF. So this is 0.26699. So we can get the value of delta G from this equation, which comes out to be minus 51511.7. So this is the calculation of delta G. Now next we come to delta S, which is given by NF del E over del T at constant pressure. Now we know the value of N, we know the value of F. We have to calculate del E over del T. Now del T is difference in temperature, 303 minus 293, which is 10. So to get this value, we have 2 into 96500 into 0.26699 minus 0.2669 divided by 10. So we get the value of delta S, which is 1.737. So from this we can calculate 1.737. This is the value of delta S. The third calculation is of delta H. So we can, if we know the value of delta G and we know the value of delta S, then delta H is given by delta G plus T delta S. So we know, we have just now calculated the value of delta G and delta S, and what will be T? T will be again 293 kelvins. So from this we can calculate the value of delta H. So this is the numerical on how thermodynamic parameters and the cell potential. So the only problem in this numerical is to calculate the value of del E over del T. So to calculate this, the two cell potentials will be given. So that is how we are going to do numericals on thermodynamic parameters. Now we can discuss another numerical based on how to calculate the equilibrium constant. So calculate the equilibrium constant between of a reaction, and the reaction is Ag plus Zn giving Zn plus 2 plus Ag. So this is the cell for which we have to calculate the equilibrium constant, and E naught cell is 1.56 volts. So to calculate this, we take log K is equal to N E naught over 0.0591. So N is again 2. So 2 E naught is 1.56 and divided by 0.0591. We can get the value of log K, and whatever is the answer, we take anti-log. This is 52, so we take anti-log. then we can get the value of K. This is how we can calculate the equilibrium constant for a reaction. Now we take up another numerical that is based on Nernst equation. We have Zn and Zn plus 2. Zinc is undergoing oxidation. The concentration is 0.2 molar concentration. The other is Ag. The other electrode is of silver. The concentration is 0.002 molars and silver. This is the cell, and we have to calculate the cell potential. The standard cell potential which is given is 1.56 volts. So for this, first we write the Nernst equation, and the Nernst equation which is written is E cell is equal to E naught cell plus 0.0591 N log Ag plus square divided by Zn plus 2. So this will be the Nernst equation. If I substitute the values, this is 4. 1.54 plus 0.0591 divided by, again the change of electrons will be 2. So 2 log 0.002 whole square. We are again doing it whole square just to balance the equation, divided by 0.2 volts. So this is the numerical. If we calculate it, we get 1.401 volts. So this is how we can calculate the numericals on cell Nernst equation. But we have to remember, in all the numericals of equilibrium electrochemistry, we have to remember two things. First is the metal which is having higher reduction potential will be reduced, and the metal which is having lower reduction potential will be oxidized. The second thing to remember is when we are writing this Nernst equation, because here we get confused what will be taken in numerator and what will be taken in denominator. So whenever we are writing Nernst equation with a positive sign, the metal which is taken at the cathode will be taken as a numerator, and the metal which is taken at anode will be taken as a denominator. So these are the two things which we have to remember while we are doing numericals on electrochemistry. Okay, so this is all in for today. Tomorrow I am going to in the next lecture I am going to discuss the concentration cell and batteries. Thank you.